talked about the most recently, getting to the algebra of the derivatives through limits. I want to go back in the beginning to go back to the to this. So data, function given as data, and then the average velocity is computed from that data. Okay, so time is changing incrementally, and then the same as location too, but you can think of location as a sampled, you sample location. So literally you take a reading every now and when according to the schedule on left of time, and you record it. Okay, then you take that table and then you can apply this little formula over here. Okay, so the average rate of change, the slope of that line, or whatever the term that you prefer, and that's how we get velocity. And very nicely, you can plot it. Okay, even with not a lot of data, you can plot it on the right, as you can see. Okay, okay. So, but there is more to it. If we are to study motion, then this is what I'm talking about. Acceleration. So we can build velocity from location. What about acceleration? So let's before doing the spreadsheet again, let's look at this data. Okay. So okay. So that's what the readings are right at the top. Readings are at the top here. So let's suppose we just have 3 readings. The initial reading of the odometer, and then after 1 hour, after 2 hours. Okay. So, and then we computed the velocity, or the average velocity for those two periods of time. So 3 sample points, locations, gives us two velocities. Okay, 35 and 65. So, well, just looking at this data. So this is the data here. Let me put it in the box. Then the computations produced more data. Okay, so let me put it this way. So original data. Then computed data is this. And now the question is, what's acceleration? Well, first of all, how do you understand acceleration, if you have an idea? What's the meaning of acceleration?
Distance over time squared.
No, not that simple. Actually, if think about the term, you are accelerating, you are increasing, or potentially decreasing your velocity. Okay, that's the meaning of acceleration. The answer is the rate of change of the velocity. So that's the theoretical answer is the rate of change of the velocity. At the very least, you can notice that what has happened during the 2-hour trip is that the velocity has changed from 35 to 65. So, well, that will be roughly the idea of what acceleration has been like. It is changed from 35 miles an hour to 65 miles an hour. Okay, and so then acceleration will be is this time you have 1 hour interval. It is actually not a 2-hour interval because there are 2 consecutive intervals of the velocity, and during the first one the velocity was. Now that's the only data that we have. We don't really want to look at the location. We want to see what has happened to the velocity, and it has changed from 35 to 65. In the first hour, 35. Second hour, 65. This is actually a 1-hour period for the acceleration. Okay, so it's changed, roughly speaking, if in the middle of the, we decide that in the middle of the first hour, the velocity was like 35, and during the middle of the second hour 65. So that's how I compute. I do 65 or minus 35, the last velocity minus the previous, and divide by time, which is once again is the length of period. So as you can see, then the acceleration will be 30, and indeed the dimensions will, but this is miles per hour. The numerator is measured in miles per hour, denominator is measured in hour, so indeed the units will be miles per hour squared. Okay, so, but as you can see, we're not computing it by looking only at the location. You could work it out and express your average velocity is what we're talking about in terms of locations. That's no problem, but really it is a better idea to think of a two-step procedure from location to velocity, from velocity to acceleration. Okay, so and that's the number that we're looking at. The key here to appreciate what has happened is to realize that not only it is a two-step procedure, the two steps are identical. Okay, so the velocity is the rate of change of position, the acceleration is the rate of change of velocity. Okay, the formula is exactly the same. So as you can see, that's the change of location or change of time, and here change of velocity, the numerator, over change of time. Okay, so that's roughly how it works out. If you have a longer period of time, so you sample more often or more time, many times, then you're going to get more numbers, and that's what I want to do. I want to do that with the data that we got. Okay, so the first row is the first chart is the position. As you can see, we see kind of driving back and forth. And yesterday we looked at what the graph on the right tells us about the original graph as well as vice versa, because sometimes you know your location and then you find velocity, but then often you know velocity and you know how your position has been changing. Okay, so either way. But then acceleration is actually in a way from the point of view primarily of physics. The acceleration is more important. Why? Because acceleration is force, roughly speaking. The laws of Newton tells that the force is acceleration times mass. Okay, so which means that that is the setup. If you're looking at anything, looking at any kind of physics situation, there are forces that you know are involved. You're pulling, you're pushing, gravity, all kinds of levers, or springs, strings, and then that is the setup. That gives you the force, and with the forces, then you figure out the acceleration. From acceleration, you figure out position, velocity, and then position. So you're working your way backwards. So let's do that. The formula, as you can see, is this. Okay. So what I'm going to do, I'm going to do exactly the same thing. Well, let me first do something here just for convenience. I will copy time in order to emphasize the point that ultimately the velocity is also a function, okay, all of the same variable. So it's equal to this. Okay, so I'm not going to do anything. I'll just copy the velocity. I'm sorry, the time for our convenience. Okay, so let me separate these so we wouldn't have to. Okay. So as you can see, the location is the first two columns, and the velocity the next two columns. So now I'm putting one more separation, and the next one will be the acceleration. Okay, so once again, what's going to happen is, so y is equal to f double prime of t is what the notation for the second derivative is, the derivative of the derivative, and then we work out what do. Okay, so let me take this. Okay, so this is going to be acceleration. Okay, and then let me. So as you can see, I cannot put the acceleration here in the very beginning of the time period, nor even here, because I don't have enough information. I have to have at least two data points for the velocity, so I have to start even here. So every time I do rate of change, I have fewer and fewer data points by one. Okay, so this time I'm going to start over here. Into this. Okay, so I'll just copy. So you see what happened was I didn't want it to plot to type that formula again, but look at it. It's the same formula. It's the same formula for the acceleration. I'm computing the rate of change, but this time it applies to velocity. So let me show it again. So this is velocity computed in terms of the location, 4 numbers. Okay, now I move 2 rows to the right, and this is acceleration computed in terms of velocity. Okay, so what remains is just to have the whole data computed, and then plot it. Okay, so let me plot the acceleration. Well, can you say anything about the graph of the acceleration before I plot it? So don't look at the first graph. Once again, 2 steps. So the first graph does not reappear, nor the data. So the new graph will be the graph of the acceleration of the rate of change of the velocity. So the second graph, maybe I should just make it clear. So this is location. Okay, and this one is velocity. Okay, and then I'm adding one more. So look at, say, this part about the velocity. So what does the acceleration look like?
It'll be negative.
It will be negative, right? It will be negative because it is decreasing. The velocity, we're slowing down, the velocity is decreasing, and then even hit 0, that doesn't really matter. It will be continue to be negative up until this point where what happens? Right, but at that moment it becomes 0. So acceleration becomes 0 at some point, and then it starts to accelerate forward. Okay, so let me plot it to confirm. Okay, so that is my acceleration. Okay, so this is the 3-step thing. Yeah, so as you can see, it started negative, continued to be negative. It is when this point, well, let me once again align these in order to see the patterns of behavior. The graph looks, by the way, very similar, so which might be misleading, but as you can see, they're not matched up. The bottom point here does not correspond to bottom point there. What does it correspond to? This point.
0.
To 0, right? See, it crosses the x-axis here. Same here. The highest point does not correspond to the highest point. It corresponds to this 0 over here, 6.5, roughly, correct. Lowest point, 9.5. Yeah, that's where my acceleration hits 0. Okay, so that's what we discussed yesterday, the relation between the location and velocity. Now the same exact relation between velocity and acceleration. Once you get down that road, you realize that it's really that step is really what's important, not the meaning of every function that's involved, location, velocity, acceleration, fine, but really it is that transition step that from one to the next, which is we call the rate of change, is what matters. Okay, and that's why we study functions in the abstract rather than in a more specific way physics. So we're studying mathematics. But it does make sense to mention certain things that why we don't stop here. So as far as modeling is concerned, so you have a specific setup, you have specific forces. Well, we're not there yet. In a physics setup, you're going from right to left, not from left to right. Okay, so we'll discuss that later. But at this time, these are the three concepts that we care about the most. And the point is, however, that beyond modeling, we actually want to know that things happen exactly with absolute accuracy. Okay, with infinite accuracy, if you like. So that's why these points, you see those dots, these are the only data points that we have for plotting. So whatever happens in between is a guess by the computer. Okay, so if we want to do theory and we want absolute precision, then we have to do limits. So that's what we started doing yesterday. Not, as you can see, we didn't get to the limits yet, but that's what we're looking at, and so let's continue with this. The difference quotient. Function is given. Okay, so we pick a point, say x, and well, let me actually, maybe I'll just put a x. It just sounds like it is a variable. Let me put an a here to emphasize the point that it is the point is fixed, and we're gonna be doing limit around that point. A plus h. Take it. Okay. So it's a function, but function of h. Okay. So we vary our step. This is the step from a to a plus h that we make, and then we watch. So that we make that, and then we watch this. Watch what happens to y. This is y. The change of y always what we're looking at. And in the meantime, something is happening to x. X forces y to change. But we're not looking at function itself anymore. There is even though we're still looking at the graph of the function, we created this difference quotient, which is a totally new function. And in fact, it's a function not even of x anymore. It's a function of h. Okay, so once again, h is the step from a. Could be positive or negative, to the left or to the right. Okay, so and that is exactly what we just saw in the spreadsheet. This thing was computed exactly that. So except probably I was using more like this formula, even though it's the same formula, but the change of y over change of x. So that's what I want to emphasize. Change of y or change of x. We know that it is the slope of that line through those 2 points, not the line, the curve itself. As you can see, there is no curve. I intentionally remove the graph of the function where it is. It doesn't matter because we only know these 2 points. So the points are f of a and b and a plus h, f of a plus h. Okay. Okay. So what do we do with this? We compute it. So the kind of exercise you might encounter is exactly that. Computing the difference quotient of this line as an approximation of something that the derivative that we are after, and then numerically improving those numbers by making h smaller. So make h small, improve your approximation. Okay, and then the last step is to do the limit. To do the limit with h going to 0, which is supposed to give us the exact rate of change, not the exact but instantaneous rate of change. So these are all averages. average rate of change, average change of y, average change of x. Well, it is exact. It's not the average. This is the average rate of change. The average rate of change is change of y or change of x over an interval. In this particular case, the interval that I'm referring to is this, from a to a plus h. Okay, and then what? And then we would take the limit with h going to 0, and that's supposed to supply us with the answer. But let's first make a picture. We did a little bit of that yesterday, and that is the what is the if we do have the graph of the function available, then what does that line look like? Okay, so even though we only need 2 points from the graph, but since we're doing the limit, it means that we're gonna need all of those points, all possible points. So if I make a bigger picture, so suppose this is my point A, and this is my function y equal f of x. Okay, then 1 point is not going anywhere. This is the point. Okay, so this is A, and this is f of A. And then I start with the x-axis always, so there will be an interval here on the x-axis. Let me start large, and so this is my a plus h. Okay. And then this is my second point, right here. And this is f of a plus h. So if h is fixed, this is the whole picture. We don't have anything else. We are talking about, once again, the difference quotient. We will be f of a plus h minus f of a over h. H is naturally the run, and rise is the numerator. Rise and run of what? Of this line. So it's the slope of this line, called a secant line. Which stands for cut. As you can see, it does make sense somewhat that to talk about a cut is cutting through the graph. Okay, so that's why what we're after to begin with as an approximation. Okay, so in this one is my change of y. Okay, so once again, this is the rise, and this is the 1. Okay. And now we start sliding. We start sliding. So sliding what? A plus h start to move towards a. So h is going towards 0. So we let it happen slowly rather than instantaneously. So you remember, it is an infinite process, and we already did it numerically. So at this point, we wonder about geometry. So what happens is the right point will move. Let me see if I can grab it. Okay, where's copy? Hold on, where's copy? It's not here. Okay.
I think it's a different hole.
No, I just looked at it and didn't see it.
It's right under your mouse.
Okay, copy. Okay. Okay, copy, and then I'll slide here, and I put it here, paste. Okay, so same story, but I'm gonna move the point, right? So that orange point will be elsewhere. So I'll raise the point, because that is very it is how should I put it, temporary. I mean, an infinite process, and this is just one point of many. I just want to kill this one. Okay, so this is gone, this is gone. Okay. Okay, so we are back to our function, but this time let me pick a point elsewhere. So I'm picking point here. So this is still a, but this is a plus h has changed. And so this is my new point. So on the left, nothing has changed. As you can see, this is the picture. Nothing has changed. And in the meantime, this becomes my f of a. The rise changes too. So okay, so my rise is this, and this is f of a plus h now. Okay, so well, let me erase this too. Let me pick a different color. So this is there is a change of the line. So it passes through the same point, but as you can see, you see what has happened? It rotated. So it's still cutting through 2 points on the graph, but it has rotated which way? So from it is clockwise. Clockwise. So it appears that the slope has decreased. Okay, and then you just keep doing it the same, pretty much the same procedure. But it is important to remember where it comes from, and then just carry out this process a little bit until the point that you realize that nothing is changing anymore. Okay, so let me do it one more time, and it's gonna be I'll pick a point really close. Okay, so once again I have to erase this stuff again. Okay, so I'm going to put the orange point, I'll put the h here somewhere, let's say. This is a, and this is a plus h, smaller number. So my point then is this. So and then once again I have to draw a line through these 2 points, so that part doesn't change. What changes is exotic color. How about this one? Oh, that's a nice one. I can barely draw a secant line through 2 points. It's barely can be distinguished from the graph of the function itself. Okay, a plus h. So that part works out just fine. So there is no change in the theory, and if you zoom in, it is really pretty much the same thing. But as you can see, that segment of the secant line between 2 points, not only it becomes shorter and shorter, but it also merges with the graph eventually. It merges with the graph, even though it's never equal to the graph, because still remember the hypothetically the function has some curvature in it. And you can never have a curved line, a straight line, be exactly equal to each other. So there will be, if you zoom in, you always have this, okay? And so they are separated, but you can, if you are doing the same roughly proportions, then you're gonna eventually lose any separation between the 2 curves. But let's realize why the question is, why not to jump in and just have the answer right away if we are looking for a line that gives you instantaneous rate of change. So if I zoom in on that point that looks like this, and this is my point, so I'm looking for something like this. Well, the problem is that there's only one point. There's only one point that we know is there. Okay, so and we cannot draw a straight line through one point. So that's why we need 2 points. 2 points determine a straight line. We can compute its slope, and that part works out. But with only you cannot say, we throw these words around it sometimes, infinitely close, infinitely, but really, if it is the same point, it's one point. So you cannot, if you try to draw a line through a point, there are infinitely many points. So which one? And the answer is very specific one, the one that we acquire through these through this operation. So let me, well, maybe just for, let me do this. Let me merge them. Paste. Okay. All right. So let me. Yeah, I think it would be interesting. So this is the number 1. Now let me take number 2. This one is number 2. Okay, number 2. Copy. Paste. Okay, so I'll just put it on top of it, hopefully. Almost. Which one is it? Okay, that's not bad. So number 1, number 3, and then wait a minute. This is these are number 1, number 2, right? So the dark green is the first one. The light green is the second one. Now let's add the third one. This one. So you can see a process. Ideally, you can have some kind of a like animation. You can find animations online, as a matter of fact. So if you want to, so you remove H small, and you can see how the secant line is changing, and the point is then to realize that what's happening is sometimes it's tempting just to say that the curve is moving, but it's not really the secant line is moving, but it's what's really happening. Okay, that's pretty close. What's really happening is rotation. Okay, so if you look at it now, we're not looking at the segments. That would be very dangerous, just to look at the 2 segments and rather than the whole this whole straight line going through. So because it becomes shorter and shorter, and then the information is being pretty much lost. But if you look at the whole straight lines, they all pass through that red point. That is the point of our interest. Okay, so this is the point here. This is the point. This is its value. This is the input. This is the output. And we are studying one point at a time, just like always with limits. It's one point. We could compute all the limits simultaneously, but early on we do it one point at a time. And this is what we're seeing. And that what we're really seeing here is the rotation. So like this. We're doing rotation, and then even the blue one already gives you a kind of suggestive to what's happening. Is the next one will change even less. So if I make H even smaller, that point will be closer to A, and the line will turn clockwise a little bit more. But at some point we're getting closer and closer. The change will be imperceptible. Okay, so and that line, once those lines start to accumulate, they are not running anywhere, these lines, because they have the same anchor, that point in red. They all rotating around it, and at some point it starts to sort of accumulate. Those lines stop changing, and then you know that your approximation has been successful, and the line will look like. So let me try to draw it, and not too big, like this, like this, like this. So this one is called the tangent line. Which stands for touch. Unlike a secant line that cuts, you can see these cut through the graph. This one touches. I mean, if it was not touching the line, then it would not be the limit of those those secant lines. Okay, secant lines, two points merge, right? So those orange points converge towards the red point, which means that the tangent line should have, roughly speaking, only one point in common. They could have some weird behavior, and we will look at some of the exceptions, but general idea is that it is indeed touch, and at least in the vicinity of this point, there is only one point in common between the graph and the tangent line. Okay, but it is still a straight line. So we have reduced then. Let me plot the sort of outcome one more time. Okay, so let me erase what we don't care about anymore. This one is gone. This one is gone. Okay, so a plus h is gone, and let me try to. I don't think I can erase this one. You need some super accuracy. So my secant line is, my tangent line truly kind of touches like this. Okay, so that's the touch. The graph is separating on the left. The graph was separated on the right. Then later on they might meet again somewhere. That's not our concern. In the vicinity of this point, they are not supposed to meet again. Okay, and that's one way to look at it. Another way is to zoom in on the point. So then it will. Then they become truly indistinguishable. So the the graph of the function becomes a straight line like this. And what is that straight line? It is the line of it is the tangent line. So wrong color. Well, I hope you know what I mean here, right? So the point, the old graph of the function, and the graph of the tangent line, and they're indistinguishable. It's almost like asymptotes. Remember, the graph of the function sort of merges with the graph of with the asymptote. Say horizontal asymptote, for example, and then they become indistinguishable. But those typically have no points in common. Say 1 over x, and the x-axis they never actually intersect. These two do have a point in common, so that red dot is still here. Okay, so that is the geometry that we care about, but it might be time to now to do algebra. And actually find those limits. We already have all the tools of limit computation that will allow us to finish these. However, it is they're on a more complex side of all the limits that I have seen. These are these are technically producing determinate expressions every single time because it is rise over the run, right? And what is happening is rise going to 0 and the run is going to 0. Once again, look at these pictures. The run is at the bottom, h going towards 0. What's happening to the on the y-axis is also going to 0. So right away we get this problematic limit. Certainly not the simplest kind when you have 0 over 0. Okay, so let's pick the simplest example that we can easily handle. And that is, say, f of x is equal to x squared, and at a, the point that of our interest is, say, 1. Okay, so it is still a good idea early on, even though we're doing algebra, looking at the graph probably is okay. So 1, 1. So a is equal to 1, f of a is equal to 1. Okay, so this is y equal x squared, and then we make a step h to the right, and so we have 1 plus h, the other number we have to worry about, and then we compute the value of the function, which gives me what? It is 1 plus h squared, right? So we compute the value of the function at 1 plus h, so we have 1 plus h squared. So then difference quotient is, we subtract, so rise over the run, change, what is the change of x is h, right, from 1 to 1 plus h, so change is x, h, okay, and then the numerator is we're changing from 1 to 1 plus h squared. So it will be 1 plus h squared minus 1. Okay, so it is possible to, but first of all, this is it. So this is a function of, it is a function. Two things to notice: that first of all, function of h, not x, and secondly, this is definitely not f. Okay, so we had function f, we build a new function. Okay, and even the variable is different. Okay, so once again, we realize that we have any determinate expression. Both of these go to 0. We know that we are looking for making that h in green smaller and smaller to move from secant line to tangent line, and so we have technically the indeterminate expression 0 over 0, which we can handle. So we cannot apply the difference quotient, so that's just the difference quotient rule, no quotient rule, because if the limit of the denominator is 0, we cannot apply the quotient rule, period. Okay, so remember what the answer is. Either general or specific. Oh, yeah, general or specific. There is one general answer, and then we do it specific. Or how do we handle indeterminate expressions? Factoring to begin with. In this particular case, we don't even have to factor, but general answer is algebra. You don't know. It might vary, and the factoring might not necessarily work. You don't know ahead of time, so there are complex situations. When you have some exponential function, or you have trig functions, that will come up too, and so you don't know really ahead of time. But that the general answer, if you have indeterminate expressions, try to apply algebra, modify what you've got, so that it's not going to be an indeterminate expression anymore. Okay, so I do algebra. In this particular case, it is even simpler than the factoring, because I just can expand. I can just expand the first term and see what happens. And the good news is, if function is well behaved, it will work out every time. So it will be 1 squared plus 2h plus h squared minus 1 over h. This one, once again, this happens every single time. The terms without h will disappear. So every time you're computing the derivative from the difference quotient by the limit, it just has got to work out, unless the limit doesn't exist in the first place. But those are exceptional functions. So that free term, the one without h, just cancels. It will every time, and then you're left with something that we can handle very easily. We just divide by h, right? So what do I get? 2 plus h goes to 2 as h goes to 0. Okay, so the answer is 2. Okay, so the computation gives the answer to what question exactly? It is, let's review that. What is the meaning of this 2? We know that it's the slope of the tangent line, but it doesn't have to be. So there are multiple interpretations. One of them, if you can always, you get a new concept, circle back to whatever you find the most comfortable metaphor for the mathematics outside of mathematics. So it's either what we have done is motion. So then you're talking about your original function is location, and your answer is the location. Okay, so location is a function of time. T is time. X squared is location. So you know that you're going faster and faster. Okay, and then your derivative, slope of the tangent line, will be the velocity. Velocity at time 1. So after 1 second, what's your velocity is? It turns out to just like 2 feet per second. Okay, so that's the one place to go, once again, to get something tangible behind these new abstract concepts. So either you go with motion, if you feel that makes more comfortable, or geometry in a pure sense. You just draw, and if you give it some thought, it is actually a very geometrical idea. What we just discovered is that the line that we found the slope, but if we know the slope, we know the line too, because we know what the point is. So this is 1. It's certainly out of proportion, right? So we know the slope is 2, and it passes through the point, slope 2, point 1, 1. Okay? What's the equation of this line? How do we find the equation of a straight line from the slope and a point?
You would plug it into y equals mx plus b and then solve for b.
Yeah, you could. Now, I mean, what I was driving at is the point-slope form, but it is really that simple. If you don't remember point-slope form, do what you just said. Okay, so but, if you do, then you save like maybe 3 seconds of your time. So I will. So I'll save it. So it will be y minus 1 is equal to 2x minus 1. Okay, so that's where they go. The slope goes here, and the 1 and 1 go here. Okay. So y minus the y coordinate of the point is equal to the slope times x minus the x coordinate of the point. Okay. So anyway, and then if you plot it, you will see. As we did, remember when we did zooming in some time ago. Not this one. Well, more like this one. As you can see, if you zoom in on that point at 0, this is a sine. This is sine, so the function is certainly is curvature. But if you zoom in on that point at 0, this is going to be a straight line, and what that straight line is, it is the tangent line. Okay, so that's, like I said, when they're becoming distinguishable, the curvature becomes invisible, and the two lines, the straight line and the curve, merge together. Okay, so that's what's behind this thing, and now maybe a good place to take a look at where this came from. It certainly application to physics, and motion is very nice, but it dates back from before finding tangent lines. So finding tangent lines is really not a physics problem. It is a mathematical problem. So given a curve and a point, find where the tangent line is. First of all, what is the point? Well, why do we need a tangent line if it's not about physics? Well, one is, how about its optics? So you know the law of optics. You know the law of optics? How the rays of sun or light, how they are reflected. Remember? So suppose this is a mirror. How do we reflect? It is determined by this angle. It goes off at the same angle. Okay, so angle of incidence is equal to the angle of whatever. like this. Okay, so that's the same angle. So it could be a ball bouncing off a wall, or like maybe in the pool when it bounces off the walls. The rule is the same. So the angle of that it is approaching that surface will be the same as it leaves it. But now, what if we have, as it's often the case, we have so like I said, so it could be optics, or it could be just any kind of motion that does not really involve any physics in terms of like forces. There are no forces. It just goes at straight line. How fast doesn't matter. It's just all we know. We want to know which way it's going to bounce. So the mirror could be curved. Okay, so if we know that the light hits it at some particular point, how do we know which way it bounces off? So what do we do? Well, we already know what to do. You know, the particle of light is so small that you can think of it as if it's hitting one single point of the mirror. But it doesn't mean that that point does not have a slope. And that slope is the slope of the tangent line. So if you know what the graph of the function is, you find the tangent line, and then it is as if your light bounces off that tangent line. Okay, just like in that last example. Okay, so there you go. Something fairly practical question. In fact, the it goes so far back that there is this legend you may have heard of Archimedes, who when his city of Syracuse was besieged by the Romans, he built mirrors to set the ships of Romans on fire. And how do you know? It is you have to collect the light into one point. And in fact, that's the mathematics that you'd have to investigate. It is in fact, well, big surprise, it's actually a parabola. So the light comes in at a doesn't matter what the angle is. It could come in any angle, but what happens? So this is the light coming in, but they're parallel. And where do they end up when they bounce? That is so special property of the parabola that they end up at its focus. So there is a focus somewhere, a special point every parabola has. And what do you know? All of these lights reflect at exactly the same spot. Well, whether the story is true or not, that's a mathematically very pleasing answer when then there's a perfect curve that solves this problem perfectly. So if I want, that's the ship. Can I redirect all the sunlight to one particular spot? And the answer is you need a parabolic mirror. They may have built it from like shields or something like that. So if it is a true story, and as that's the so they were able to construct tangent lines just like this, just like that. You need to note all the tangent lines of the parabola in order to know where the light bounces, where it will be reflected, and then so they knew how to do it. Okay, and you might think, what if do you remember modern examples of use of this? Anyone? Headlights. You put the light in the focus, and it is, which is a point, okay, and then it is reflected back in a beam of lights, which is all parallel lights rather than like this. Okay, so that's the application, and once again, it's what's behind it is just a bunch of tangent lines that you need. So that was a long-standing, had been a long-standing problem, how to find tangent lines for a given curve. So once again, this is like 2,000 years ago or more. Okay, and then another problem is fairly easy to do it for a circle. So once again, a tangent line. So once again, what if my mirror is circular? Where is it going to bounce? So to answer that question, you need to find a tangent line. Fortunately, it's not too complicated. If you know the center, then what do I do if I know the center? How do I find the tangent line?
Would it be the diameter and the radius?
Well, I build the diameter, but then what? You see what's happening? So this one is, let me make it red. So this is the tangent, and this is indeed the radius. What's the relation?
Perpendicular.
They're perpendicular. So that's the key. So if you can build right angles, you can draw tangent lines to the circles. So once again, it also goes back to Greeks. So they knew how to deal with circles, how to deal with the parabolas. Okay, so it reflects parallel lines reflect into the focus. Then they also had ellipses. And ellipses is a nice thing, also nice property. It actually reflects from one focus to the other. Okay, so that like this. Okay, and in fact, you may have you heard of the chamber of whispers, ever, or something? I don't remember the exact name, but it is a circular, not circular, elliptic room, maybe a very large room. But if you're standing in one focus, you can hear what some other person very far away is talking about if he is in the other focus. So there might be a very large room, so you're not supposed to hear it. You can also, hypothetically, you can have objects or obstacles between, like, I don't know, a tree. It doesn't matter because the light will be there speaking in whispers, and you still will be able to hear it. So that's, I remember I saw it somewhere. So all of these go way back to the Greeks, and then that's the start. Then there's a parabola with also a parabola, hyperbola, ellipse. Hyperbola also has interesting properties, and then they were trying during this 17th century and before to build more and more different curves, to handle more and more curves in finding tangent lines. And then Newton actually made that he faced that problem, and how to find the tangent line for any curve. Okay, and he solved it. Obviously, had solved it. It's still not every curve, but every reasonable curve that we can think of, we can find a tangent line. How? By differentiation. This is like this. So it is certainly a parabola, but we could have made a function way more complicated, still be able to work out the tangent line at every single point, and at some point at all points simultaneously. So, but then it turned around. How he understood tangent lines is through motion. So that's where we start with motion, and then we proceed to tangent lines, but you can go backwards from tangent lines, and then you understand them through motion. So you're moving on the x-axis and on the y-axis, and how they change with respect to each other gives you the instantaneous rate of change, and that's the slope of the tangent line. Okay, so this computational thing is certainly big because it tells you where things come from. So this is a typical example that frequently asked to find the derivative by nothing but from the definition. This is the definition of the derivative. Well, I guess I probably should just give that definition. So definition. So given a function y equal f of x and a point x equal a, the derivative of y equal f of x at x equal a is this limit. In other words, it's a number. Sorry. And this is the notation. So we indicate the point we were talking about, A on the left, and we indicate that it is something new, that little prime, it's called the derivative, so we are deriving a new function from the old through this limit. Okay, so what we just did, the example that we carried out was computing the derivative from the definition, in other words, as a limit. So this is definition. You can see it's still rise of the run, and then the limit with the run going to 0, and that is the limit. It gives you the slope of the changed line, also known as the instantaneous rate of change. All that. So the expression itself gives you the rate, the average rate of change, and with the limit going towards 0, h going towards 0, it is then, that's where instantaneous comes from. Okay, so there will be more examples. Let me do maybe one more example of computing from the derivative, derivative from the definition. Say, find f prime of a when f of x is equal to, well, let me give you slightly more complicated. How about square root of x? And a is still equal to 1. Okay? So, alright, f prime of a, the formula right here, limit, h goes to 0. Now I substitute, so it's gonna be square root of 1 plus h, right? So that's the first term of the numerator minus square root of 1 over h. Okay? We can repeat that every time, even though it's not necessary. I guess that this is the indeterminate expression. Quotient rule does not apply. So, and the answer is always the same, algebra. So, indeterminate expression, no quotient rule, algebra. Okay? So we gotta eliminate the indeterminate c from the expression, and the answer is by means of algebra. So I'm not ready to apply any rule of limits, because, well, it's for as long as the function the expression is indeterminate. Okay, so I have to simplify it. There is a trick, if anybody knows the trick how to simplify this. Divide and multiply by what we call the conjugate. So it's the same expression, but with the plus sign. So it's what we're doing is the opposite of the there is no h here. The opposite of factoring. Okay, so I'm multiplying by 1. I'm multiplying by 1. That fraction is 1, but this is the conjugate of that. So square root over 1 plus h minus 1 is that expression that is a irrational expression with the square root. So we find its conjugate, which is simply replacing minus with plus, and then we multiply by 1 with the same numerator and denominator. The point being, if you can see what can you see what happens to the numerator? What happens to the numerator? If we multiply these two. On the left I have the difference, on the right I have the sum. Remember the formula? Difference times the sum. A minus b, a plus b. well, let's write it out. A squared minus BA plus BA minus B squared. A squared minus B squared. Okay, just doing the distribution. So that is an abbreviated multiplication. So you just save some time, and then if you save some time, you sort of plan ahead, and you know what that is going to be simplification. I want to that square root over there that stands in the way in the numerator. So how do I do it? I want to square it, but in such a way that I don't mess it up. So I multiply by the conjugate. I have a difference of squares, which will be then 1 plus h minus 1. Right? So both of them are squared, and that way 1 disappears. Right? And I'm left with h in the numerator. So h over h1 minus h1 plus 1, and then I naturally cancel h, and I have my limit, which is now simplified. Okay, what's the now? What do I do now? Well, what I do now is observe that this is not an indeterminate expression anymore, because the numerator is simply 1. Where does the denominator go? H goes to 0. Where does this thing go? To 2. How do you know? If you can justify it. Remember magic words? What?
Some rule.
Yes, but there's what about the square root? What do you do with the square root? Remember the magic words? The function is
Conversion.
no. The word is continuous. So the function is continuous, and that is why you evaluate the limit by substitution. Okay, you can actually justify also, we talked about that y square root is a continuous function to begin with, and the answer is it is the inverse of x squared. Okay, and the inverse of a continuous function is a continuous function, roughly speaking. So the answer is 1/2 then. So like this, after all this work, you can actually see the result. This is 1, and this is my secant line, tangent line with slope 1/2. Okay. All right. So tomorrow.